The MiG-41 project represents one of the most ambitious and technically challenging endeavors in modern aerospace development. Intended to succeed the MiG-31, it is envisioned as a hypersonic interceptor capable of operating at speeds around Mach 4 and at altitudes approaching near space, significantly extending the boundaries of current manned aviation. This aspiration, while groundbreaking, is coupled with an array of profound engineering, material, and logistical challenges that must be addressed to transform the concept into an operational aircraft. At the forefront of these challenges is the extreme thermal environment encountered at hypersonic speeds. When an aircraft travels at speeds exceeding 4 times the speed of sound, the friction between the air molecules and the surface of the aircraft generates immense heat, often reaching temperatures that can weaken or damage traditional aerospace materials. This necessitates the development and integration of specialized materials that can withstand sustained thermal loads without excessive weight gain, which itself can degrade performance. Advanced ceramics, ultra-high temperature composites, or novel metal alloys are potential candidates, but manufacturing them at scale, integrating them into an airframe, and ensuring their reliability remain major obstacles. The design of the airframe must carefully balance several competing factors. It needs to provide sufficient structural integrity to endure the stresses of hypersonic flight while maintaining aerodynamic efficiency and minimizing weight. Aerodynamically, the shape of the aircraft is crucial to reducing drag and managing shockwaves generated at such speeds. Precision in shaping is essential to avoid turbulence that could destabilize the aircraft or increase fuel consumption dramatically. Additionally, because the aircraft will operate at altitudes nearing the edge of the atmosphere, where air is extremely thin, traditional control surfaces become less effective. To address this, the aircraft may require alternative control mechanisms, such as vectored thruster reaction control systems, to maintain maneuverability in low-density air. Propulsion is another critical area presenting considerable challenges. Conventional jet engines struggle to function efficiently beyond certain speeds and altitudes due to limitations in air intake compression and temperature tolerance. The MiG-41 is expected to utilize a propulsion system capable of sustained operation at hypersonic velocities. This could mean combining multiple engine types or developing advanced turbojet variants that can handle the transition from subsonic takeoff to sustained hypersonic cruise. Engineering engines that can operate reliably under these conditions while managing the extreme heat generated remains a complex task that is yet to be fully resolved in any operational aircraft globally. Operating at near space altitudes adds further complexity. The thin atmosphere at these heights reduces aerodynamic lift, requiring design considerations to ensure the aircraft can sustain flight and perform interception missions effectively. For a manned platform, the cockpit must provide life support systems that can sustain the pilot in near vacuum conditions, protect from radiation exposure, and maintain stable pressure and oxygen levels. Alternatively, unmanned or optionally piloted designs have been considered, which bring their own set of challenges in remote operation, autonomous decision-making, and secure communication over long distances and high speeds. The avionics suite and sensor systems must be capable of rapid data processing and threat detection within a drastically reduced timeframe due to the aircraft's high speed. This demands cutting-edge electronic architecture that can filter, analyze, and respond to inputs almost instantaneously while resisting electronic interference and operating reliably in extreme thermal and radiation environments. From a programmatic standpoint, the MiG-41's development is heavily influenced by the broader context of Russia's industrial capacity and economic conditions. Sustained funding and access to advanced manufacturing technology are crucial for progressing from conceptual designs to prototypes and eventually to production. International sanctions and geopolitical pressures may affect supply chains and the availability of critical components, posing risks to the timeline and scope of the program. Historically, projects aiming to push technological boundaries in military aviation often face cost overruns, delays, and technical setbacks, and the MiG-41 appears no different in this regard. As of the latest updates, there is no publicly confirmed prototype or successful test flight. Most available information derives from official statements, conceptual drawings, and media reports, leaving much of the aircraft's actual status shrouded in secrecy. Analysts remain cautious, acknowledging the project's visionary goals but also highlighting the significant uncertainties regarding its operational readiness. Without concrete evidence of functional prototypes or demonstrator flights, it is difficult to assess whether the MiG-41 will meet its ambitious design criteria or if it will remain largely theoretical. Furthermore, there is a possibility that the program serves multiple strategic purposes beyond pure technological development, such as signaling advanced military capabilities or influencing geopolitical perception. The balance between genuine progress and projection of technological prowess is delicate and often difficult to discern. The MiG-41 symbolizes a push toward redefining the limits of aerial interception through speed, altitude, and operational range. While the potential benefits of such an aircraft are substantial, especially in terms of rapid response and extended patrol capabilities, turning this vision into reality depends on overcoming formidable technical challenges related to materials, propulsion, aerodynamics, avionics, and industrial execution. Until more tangible milestones are achieved and made publicly known, the MiG-41 remains an ambitious project whose success is contingent on bridging the gap between cutting-edge aerospace research and practical deployment under the constraints of economics and technology.